So now that we have some nice activation set up via this infection solver, we can go ahead and start applying the animation from the flying creature onto these grain points. And we've been working fairly low resolution so far, so I'm going to turn up the resolution a bit. If we go to Vellum Constraints Grain, I'll turn that grain size down to 0.2. For the final sim, I believe I used a grain size of 0.1, but we're not going to turn the resolution quite that high until we're pretty confident that the simulation is all working nicely. So now that we have a few more grain points available here, right now we have 500,000 particles we'll be simulating. Let's drop in our point deform that we're going to use to apply the animation, connect our infection solver output to that. And for the rest position, we're going to use the rest position after it's been scaled above. And you could connect a wire from here to the top of your network if you want. But if you don't want to drag wires all the way across your network like that, you can keep things a little bit cleaner if you just add in a null that you can reference below. So I'll just create a null here and call this creature scaled rest. And then down here, let's create an object merge and point this to ... /creature scaled rest. And we'll put this into the rest position of our point deform. And you can use packed objects for point deforming, but that's really only going to use the center point of each packed object. So oftentimes when you're doing a point deform like this, you'll want to unpack your geometry. So let's unpack this before we wire it into the point deform. And we're going to do the same thing with our animated creature as well. Let's also unpack that, and we'll middle mouse on them to make sure that they have matching topology. So if we middle mouse the flying animation, that's 145,103 points, and middle mousing on the unpacked creature rest, we have the same number of points there. So let's put the animation into the third input of the point deform, and now we have some animated grains flying through the air. And this is working reasonably well, but we are running into some issues with the tips of these tentacles here. And the reason for that is because we don't have much resolution on the tips here. The rest of the creature has a reasonable amount of resolution for point deforming purposes, but these really long triangles don't have enough point information along them to do a good job of point deforming. So I'm going to just select these based on their path attribute, and you can hit 9 to bring up the attribute-based selection, or this little button here. Go to the gear icon and select paths. And right now this is showing up as an empty string. If we try to click on these tentacle ends here, that's because when we unpacked our geometry, we didn't transfer any attributes. So on both of these unpacks, let's go to Transfer Attributes and transfer that path. Okay, so now when we select our unpack and try to select based on path, you can see now we're able to select all of these objects based on that value. So just select the tentacles ends here, and then tab in the viewport and type in subdivide. And you can see that if we bypass the subdivide, it's only subdividing the ends of these tentacles here. So I'm going to use 2 subdivisions to make sure that we have enough divisions along the length there for the sake of point deforming. And then we're going to do the same thing to the animated version of the creature, because once again, we need to ensure matching topology between the rest and the anim states. So display the anim, and let's look at these tentacle ends. Going to paste in the same subdivide, connect that there. And now if we connect that into the third input of our point deform and display those results, now we're getting much nicer results at the ends of those tentacles when we're applying our animation. And just for the sake of comparison, if I select both of those subdivides and bypass those, you can see we have some points that don't follow nicely without it. And it's also good practice to ensure that these animating points have decent velocity data that can assist with velocity inheritance and the simulation. And it looks like this is picking up some velocity from somewhere. I'm actually not sure where that velocity is being applied. If we step up through our sim, it looks like that velocity is being applied when the grain constraints are initially created here. So we can just disregard that velocity attribute that's created by the vellum constraints grain. So we're just going to create a new velocity with a trail sop after the animation is applied. So create a trail, set the result type to compute velocity, display that, and it can be a good idea to turn on point velocity display in the viewport just to sanity check this and make sure that everything looks right. So zooming in here, sure enough, it looks like all of these velocities are working pretty nicely. Now we still need to tell Vellum to follow the animation of these points, so let's create another Vellum constraints to force these points to follow this animation. So we'll drop this new Vellum constraints SOP after the trail and set the constraint type to pin to target. The group type will be points, and we don't actually need to select a group because we just want everything to be pinned to its animation. And then scrolling down a bit, under pin to animation, let's select match animation. And now if you middle mouse on the Vellum constraints here, you can see this is adding this glue to animation attribute that will help to drive this behavior. And even though this is a Vellum constraints SOP, we don't actually need to use any constraints from the second output here. And now we have one more step before adding these grains into our simulation, and that's to set the stopped attribute based on the color. So I'll drop in another point wrangle, and I'll call this sim attributes. And I'll say if at cd.r is equal to 1, then we'll create a stopped attribute, and this will be an integer, so type I at stopped equals 0. So red means active, so the grains will not be stopped in place. Then else, if the color is not red, then I at stopped equals 3. And if you look at the Vellum attributes in the Houdini help, you can see that there are a whole bunch of attributes here that we can use to override the behavior of the sim. And there's an attribute specified in here called stopped. So if we search for that, here we go. This is pretty important because there are a few different stopped behaviors to be aware of. And as the help doc indicates, it's a standard pop particles attribute as well, but also used and respected by Vellum. And when we set the stopped attribute equal to 0, that means it's freely simulated, not affected by the animation or anything. If we set a value of 1, it can rotate, but only fixed in space. 2 means it can't rotate, but it's free to move around in space. And 3 means that the particle can't rotate or move. And with these Vellum grains, I don't think the rotations really matter very much because we're just going to be rendering them as point particles. But I'm just going to set them to stopped equals 3 so that they're completely stopped with regards to both translation and rotation. So now finally our grains are ready to simulate. I'll drop in a null called grains to sim, and let's pull our DOPNet down here. Connect the grains to sim to the first input, and on the DOPNet let's also change our start frame to 95 because that's when we've started our disintegration activation. And then let's take a look at what this simulation looks like with this animation applied. Now I've only flipbooked a handful of frames here to illustrate the problem with the simulation at this point, and the grain particles are picking up the animation, but they're always glued to the animation and they're never being activated based on that infection activation that we've set up. So in order to make the particles respect that activation, we're going to need to do a couple things inside the DOPNet. So if we dive inside our DOPNet, we can actually remove a couple things we no longer need. For example, this ground plane is no longer necessary since we're not going to collide with the ground at all. So we can just disconnect that from our simulation. And we're going to need to use a SOP solver in DOPS to activate the vellum grains based on that color in the input. So we can attach multiple solvers that will work on the same vellum object. So we have the vellum solver that's currently processing our vellum object, but we can also attach a SOP solver as well that will do the actual activation. And when we're using multiple solvers to affect the same simulation object, then we need to combine them in a multi-solver. So let's disconnect the vellum solver from the gravity, and let's add in a new multiple solver and disconnect the vellum object from the vellum solver. Let's connect the vellum object to the multi-solver instead, and then we can connect multiple solvers that will affect this one simulation object. So connect the vellum solver first, the SOP solver second, and then connect that multiple solver back to the gravity. So this vellum object will first be affected by this vellum solver here, and then we'll do extra stuff to it with the SOP solver after this vellum solver is evaluated. Now if we dive inside this SOP solver, we're going to use this to read in the activation color from SOPs and then set the stopped and glue to animation attributes accordingly. So let's first object merge in our grains input. So for this object merge, I'll point this to dot dot slash dot dot slash dot dot and then grains to sim. And this will bring in the actual input that's coming into the DOPNet. And then within our SOP solver here, we have a few different DOP imports that will read in different types of simulation data. In this case, we only really care about reading in the DOP geometry, which will give us the current state of the simulated grains within our DOPNet here. So the DOP geometry are the current simulation grains. This object merge represents the grains that are coming into the DOPNet from SOPs. So we're going to copy this activation color from this object merge onto the current DOPNet grains. And the main reason that we really need to do this is if we exit our SOP solver here, go back to our vellum source, this vellum source is only bringing in that geometry once at the beginning of the simulation. So you can see the emission type is only happening once. This isn't going to continuously read the attributes from the input. This will grab whatever the state is of the DOPNet input at the start frame, but it's not going to continually update the simulation objects based on the input, which is why we need to update these objects manually through this SOP solver. So within the SOP solver, we're going to do an attribute copy, and we're going to copy onto the DOP geometry, so put that in the first input, the object merge in the second, and the attribute copy will default to copying color, which is actually the attribute that we do want to copy, and we don't have to worry about using the match by attribute options since this DOP geometry will match the topology of our input. And then after copying over that color, we can use a wrangle to set the stopped and glue to animation attributes. So in the group here, I'll say at cd.r equals 1, and the group type will be points because cd is a point attribute. And then for all of those points that have a red component equal to 1, we're going to set the stopped attribute equal to 0, and the glue to animation attribute also equal to 0. And then similar to the infection solver that we set up earlier, we're going to add an output at the end of this to make sure that the correct stuff is outputted from this SOP solver without this being affected by the display flag. So connect the attribute wrangle there, and I'll rename this to grain activation. And while we're working on our DOPNet here, we might as well add in a couple extra forces to make the grains look a bit more interesting when they're simulated. So a bit of pop wind noise will help to make this look more interesting and organic. So we can drop in that pop wind after the vellum source. And I'm going to add a bit of air resistance in here. And because this is a fairly large scale simulation, I'm going to increase the swirl size a fair amount, increase the amplitude to get some noise in there, and we can slow down the animation of this turbulent noise by increasing the pulse length. So turning that up to 3 will slow down the evolution of this turbulent noise a bit. And I'm going to try adding just a little bit of extra detail in this turbulent noise by turning the turbulence up from 3 to 4. And of course, this may take a little bit of tweaking to get the right amount of interesting noise detail that you're looking for. And then finally, for the gravity, we actually don't want this disintegrating creature to fall down to the ground. We kind of want these disintegration particles to float away. And we're going to use the gravity to apply some wind force like we did on the particle trails for the mechanical bugs. So let's go up to the object level and go to our control null here where we set up the wind direction. So I'm going to copy this wind direction, right click, copy that parameter, and then go back to the DOPNet. And for the gravity force on our disintegration sim, I'm going to paste that relative reference into the force here. And as we saw before, this relative reference is a little bit messy here, so I'm just going to once again change all these to point to the object context instead of being a pure relative reference. And as we saw with the pop simulation, if you're not happy with the amplitude of this wind force being applied through gravity, you can add a parameter multiplier on top of this force as well, but I'm just going to leave it as is for the moment to see how close we are with the current force amplitude there. Now I've only flipbooked a handful of frames here because things are a bit broken and not working properly. Our activation is working okay. We're picking up that color update from SOPs within our DOPNet, and we are successfully activating the grains, but they're just frozen in space here. They're not affected by the pop wind or the gravity or anything else. And the reason that these grains are not simulating properly is because on this vellum constraints that's doing the pin to target, we're using the default pin type of permanent. So under pin to animation here, we have a few different pin types available. And if you hover over this parameter and hit F1, this will pull up the help for that node. And if we scroll down to the pin to animation options, this has some more information about what these different pin types are doing. So the default of permanent says it's setting the mass attribute to 0, making it a hard constraint. And because the original mass is not stored, it's not possible to release this constraint later. And in our disintegration, we need to release these pin constraints. We want to allow the simulation to take over and freely simulate this with dynamic motion. So permanent is not the pin type that we want. The next option, stopped, is sort of what we're already doing with that stopped attribute in the wrangle. And this is the option that we're going to use to fix this problem. It says that the mass is unaffected, and that allows us to restore the dynamics of the point by setting stopped to 0. So this is exactly what we want here. This soft option we're not going to mess with This will create a constraint between the point and the target location and uses stiffness and damping ratio to try to get the point to achieve that target position. And we don't really need this because we just have a pure non-simulated animation follow or a completely dynamic, freely simulated grain. So we're going to use the stopped option here. And before we flip that, you can see the problem if you open up the spreadsheet on the vellum constraints here, and then look at that mass attribute. You can see this is set to 0, and this mass of 0 is unaffected by any options that we set on the mass for the vellum constraints here. So on the vellum constraints, you have a mass parameter. This says it should be unchanged. And if you try to set uniform or anything else, no matter what you do, the mass is always going to come out 0 when you have the pin type set to permanent. This is one of those things that's not necessarily very obvious, and this can really cause some problems if you're not aware of this. So if we change this pin type to stopped instead of permanent, you can see now it's preserving the mass value of all of those grain particles, and it's now also creating this stopped attribute for us. But the stopped attribute values don't really matter that we're getting out of this vellum constraints here because we're already setting our own stopped value in the wrangle just after that vellum constraints. But this vellum constraints for that pin to target is creating the stopped attribute because that's what this is relying on to determine whether it's following the animation or not. And it is still outputting that glue to animation attribute. So I'm sure we could just set the glue to animation and stopped attributes without using a vellum constraint SOP to set them. It's up to you if you want to just set those attributes in a wrangle, or if you want to use these helper tools to set some of the attributes that you're needing for your sim. In any case, now that we've set the pin type to stopped and we've fixed that issue with the 0 mass values, now we can resimulate our grains and see some proper dynamic behavior. Now after running a flipbook with the 0 mass values fixed, we now have a pretty cool simulation here. This is looking quite nice, and this is not our final simulation because we will need to rerun this disintegration sim because so far we just have a procedural noise running through these tentacles, and we're going to use Vellum to do nicer deformable sims on these tentacles soon, and once we do that we need to rerun our disintegration effects. So there will be more opportunity to tweak and finesse the simulation once we run it with the final animation. But there are a couple things we can look at first, and one of those things is velocity inheritance. And we are also running into some kind of explosive results. In particular, near the body here we have some grain particles shooting out, and we're going to investigate that as well.